Given an integer array and an integer k, count every non-empty contiguous subarray that contains exactly k different integers. Return that total count. At indices 0 and 1 the values are 1 and 2, two different integers, so this subarray counts. At indices 1 and 2 we see 2 and 1, still exactly two distinct values, so that counts as well. 7 subarrays in total have exactly two different integers. From index 0 through 3 the values 1, 2, 1, and 3 use exactly three distinct integers. From index 2 through 4 the values 1, 3, and 4 also qualify. Only 3 subarrays meet the rule, so the output is 3. If we try to use a standard sliding window to capture subarrays containing exactly k distinct numbers, our boundary logic instantly collapses. Because identical numbers are scattered throughout the sequence, shrinking our left boundary doesn't predictably reduce our distinct count, leaving our window trapped and confused. To break this gridlock, we introduce a powerful mathematical shift. Instead of hunting for an exact match, we change the rules to count subarrays with at most k unique numbers. Under an at most rule, our logic becomes beautifully predictable, we expand smoothly to the right, and we only ever shrink the left pointer when a brand new element pushes us past our ceiling. If the window has at most k distinct values, every subarray nested inside qualifies too. When the right pointer advances, we gain new valid endings at that edge, one batch per window width. That count is right minus left plus 1. Think of it as filtering a dataset. Subarrays with at most k unique numbers contain everything we want, plus smaller sets we don't care about. Compute the total for at most k, subtract at most k minus 1, and the extra sets vanish, leaving the exact count we need. 2 sliding window passes finish in linear time. Add window widths for at most k, subtract at most k minus 1, answer 7. We initialize our sliding window. Both our left and right pointers start at the very beginning of the array, index 0. Our running total of subarrays is currently 0. As our right pointer advances through the first 3 positions, we log the frequencies. At index 2, our window holds 2 1s and a single 2. Since our unique count is exactly 2, the window is perfectly valid. We add the window's width at each step to our total, bringing our subarray count to 6. Our right pointer moves to index 3, landing on another 2. The frequency vault updates, but the number of unique elements remains exactly 2. This massive window is completely valid. Its width is 4, meaning it introduces 4 brand new valid subarrays that all terminate at this right edge. We add 4 to our chest, matching a total of 10. Now, the breaking point. Our right pointer lands on index 4, bringing a 3 into our window. Our unique count spikes to 3, breaching our ceiling of 2. The contraction loop fires. Our left pointer marches forward, dragging down frequencies and evicting elements until the card for number 1 drops to 0 and shatters, restoring window safety. With our window stabilized, we harvest our final combinations for this run. The window width is 2, adding 2 final subarrays to our count. Our first pass completes, scoring a grand total of 12 subarrays containing at most 2 distinct integers. Now, we run the exact same engine a second time, but change our ceiling to at most 1 distinct integer. This run captures only those subarrays made entirely of uniform, repeating numbers. Running this completely across our layout yields a total score of 5. Finally, we overlay our 2 results. We take our 12 subarrays that contain at most 2 distinct values, and subtract the 5 subarrays that contain at most 1 distinct value. By stripping away those single element groups, we filter down to our exact answer, 7 perfectly formed subarrays with exactly 2 distinct elements. N is the length of nums and k is the target distinct count. Time is O of n, we run 2 sliding window passes, and each index enters and leaves a window at most once per pass. Space is O of n for the frequency map, which stores at most n distinct keys in the worst case. The driver counts subarrays with exactly k distinct integers. Return at most k minus at most k minus 1. The helper counts subarrays with at most max distinct different values. Start with left at 0 and total at 0. Track frequencies in an empty map. Expand right across the array. Log the new rightmost value in the map. While too many distinct values sit inside the window, decrement the count for the leftmost value. If that count hits 0, remove that value from the map. Advance left by 1. Add every valid subarray ending at this right index. Return the running total.